Hi everyone, welcome back. So this is me coming back with the original advanced encryption standard algorithm and to discuss more about it. If you are watching this video directly, my suggestion is to watch my previous video where I explained a minor version of AES, which we call it as simplified advanced encryption standard, which is more or less having the same kind of operations, and we've performed some kind of a small example also. The reason why I suggested you to watch that video is simply because you will have a better understanding of the operations that are involved in AES. That's all. And coming back, even before we go directly to the algorithm, let me just give you or brush up a little bit of history about AES, how it came, how many proposals were there, how many of them competed to become as the advanced encryption standard. And on 2nd of January 1997, NIST actually issued a call for proposals for a new block cipher standard, which is to be referred to as the Advanced Encryption Standard or AES. They have given some certain guidelines and they asked proposals from all across the world. The primary reason why they wanted a new algorithm or why they wanted a new standard is simply because the existing one, which is called as Data Encryption Standard or DES, has become vulnerable to brute force attacks. The reason why it has become vulnerable is the practical key size of DES is only 56 bits, where they started to build machines which can break the encryption of DES in maybe at a cost of $100,000 to $200,000. So for this purpose, they wanted to have a new standard which will have the capability to withstand against these brute force attacks. And there is another reason as well. While designing the DES, it was primarily designed for implementation on hardware devices and for 1970s technology. DES is very sluggish when you want to implement it on software to support the modern day applications. So they want something new, which is not only strong enough, but also good enough to be implemented on software quickly and efficiently to support modern day applications. In this regard, after the announce of this particular contest, in the 9 months that followed, 15 different designs were created and submitted from several different countries. They are Cast 256, Krypton, Deal, DFC, E2, Frog, HPC, Loki 97, Magenta, Mars, RC6, Rijndael, Safer, Serpent, and Twofish. These are the 15 designs that were selected for the second round. And there are some certain category and criteria where NIST wanted to analyze these particular candidates. The first one is security. As I told you, the first primary thing which we are going to analyze any algorithm is how secure it is, how good it is to withstand the different types of cryptanalysis attacks. So resistant to cryptanalysis, soundness of math, randomness of output, etc. The second criteria is obviously cost. If I give you an algorithm which is very good, but if it is going to charge me more, that means I need more and more resources like memory, RAM, etc. It becomes really tough. So cost, computational efficiency, and memory requirements. The third one being the implementation characteristics. So how good I can implement this algorithm on software, how much less requirement of hardware support is needed. So flexibility, hardware and software suitability, the simplicity of the algorithm itself, the the rate at which this algorithm can compute, all these things come into play. So these three are the primary criteria through which the NIST has evaluated these algorithms. First one being security, the second one being the cost, and the third one being the implementation characteristics of the algorithm. Okay, so later on in 1999, they announced that they were narrowing the field from 15 to 5. So out of those 15, they narrowed it down to only 5 applications, which include the Mars, RC6, Rijndael, Serpent, and Twofish algorithms. All these 5 algorithms are usually called as the AES finalists and were designed by cryptographers considered well-known and respected in the community. On October 2nd, 2000, NIST announced that Rijndael had been selected as the proposed AES, and on November 26, 2001, AES was approved as Federal Information Processing Standards publication 197. So it was standardized and it was given out publicly for usage during 2001. So Rijndael, this algorithm which was selected as AES, was named after two Belgian cryptographers who developed and submitted it. The first one being Dr. Johan Damon of Proton World International and Dr. Vincent Rinman, a postdoctoral researcher in electrical engineering department of Catholic University Leuven, Belgium. So these two are the people for after whom this particular algorithm was named as Rijndael. Of course, some people rhyme it as Rijndael also, but doesn't matter. My pronunciation is Rijndael. So the AES standard states that the algorithm can only accept a block size of 128 bits. So it will accept the plain text in blocks of 128 bits, but it offers you a choice of 3 key sizes. If you remember, DES has only 1 key size. You take 64 and after the first permutation, you get only 56 bits, isn't it? So here I have a choice of taking 3. Based on the type of security that my application requires, I can select any key size. The 3 options are either being 128 or 192 or 256 bits of key size. Depending on the version you choose, the name of the standard is modified to as AES 128 or AES 192 or AES 256. If you want to go through the original publication, this is the link to the website where you can find the FIPS 197 publication of the Rijndael algorithm. And unlike the DES, the number of rounds in AES is variable. This is because if you decide the length of the key to be 128, this algorithm uses 10 rounds. And if you go for the 192-bit version of the key, then you have 12 rounds. And if you select maybe 256-bit key size for high confidential applications like military, etc., then this algorithm will have 14 rounds of processing. Each of these rounds uses a different 128-bit round key, which is calculated from the original AES key. So from the given AES key, you have to do a key expansion algorithm, which will create different and distinct subkeys for each one of these rounds. This is pretty much similar to what we did in the SAES also. SAES, I told you it uses 2 rounds, and I have shown you how a key can be developed or how a key can be expanded to give new subkeys. Now, this is the overall structure of AES. So do not get confused or overawed by a lot of things over there. It's pretty simple. There are only 4 operations that are mentioned over there. Now, to discuss this further, AES is an iterative cipher rather than a phasal cipher. The reason why we say an iterative cipher is because if you remember the phasal cipher structure, which is considered to be the backbone of many traditional ciphers, it actually divides your data into 2 halves and it modifies one half of the data in one round and then modifies the other half of the data in the subsequent round. Nothing of that sort happens with AES. What it does is the entire data block is actually processed in parallel. So whatever operations we are doing, we will do on the entire amount of the data. We don't split it into parts and we don't do it in halves. Okay. So that is the reason, that is one of the primary differences between the AES and the phasal cipher structure. So the input to the encryption and decryption algorithms is a single 128-bit block. As I told you, AES accepts the plain text. Block size is equal to 128 bits, isn't it? So which is depicted as a 4x4 square matrix of bytes. So this 128 bits is actually written as a 4x4 matrix. So 4x4 matrix gives me 16 boxes. So each one of these will be having 8 bits. That means I'm rearranging the 128 bits of your plain text into a 4x4 matrix of how many bytes? 16 bytes. Okay. So the matrix, this block is copied into the state array. This matrix is, we call it as the state matrix. And this state matrix is given as an input to each and every one of these operations. It gets modified after each and every operation. And after all the rounds of processing is done, whatever matrix we get here, understand, whatever matrix we get here is your final cipher text. So the input to the encryption and decryption algorithms is a single 128-bit block, which is depicted as a 4x4 square matrix of bytes. This block is copied into the state array, which is modified at each stage of encryption or decryption. After the final stage, the state is copied to an output matrix. This output matrix now contains your ciphertext, which is your final value. So 128 bits of plain text. This is 128 bits. And after all the iterations are done, your final ciphertext will be 128 bits. Okay. Now, the key. Let us talk about the key. AES also accepts 128-bit key. Okay. So the key that is provided as an input is expanded to an array of 44 32-bit words. So rather than looking these things as a 4x4 matrix, the key has been arranged as an array of words. What do you mean by words? So out of these 128 bits, if I take the first round key K0, we take it as, we can write it as W0, W1, W2, and W3. So there are 4 words. So each word consists of 32 bits. Your first initial 128-bit key, which has been selected by the user, will be used in your first round or round 0. In the very first operation that your plaintext undergoes is an AddRound key, where the original key is used. So dividing this, so from K0, I'm going to generate the remaining keys from K1 till K10. You can see there are total of 10 rounds, and each round has an AddRound key operation. So for each one of these AddRound key operations, you can see this. So I will start creating the 4 different words from this key. We will discuss more about how this key will be expanded and what is the operation that is involved in generation of the new keys. So for each and every one of these rounds, a new and a distinct key is generated from the original key only. Now, let me proceed on. So for both encryption and decryption, the cipher begins with an AddRound key stage. You can see in your encryption also, this is your AddRound key stage. The first operation that your plaintext encounters is AddRound key. And similarly, for decryption, the first operation that the ciphertext encounters is your AddRound key. And then they are followed by 9 rounds that include all the 4 stages. If you see properly, round 1 to round 9, that's why I colored them commonly. Round 1 to round 9 has got all the 4 operations. 1, 2, 3, 4. There are 4 operations in round 1. Similarly, there are 4 operations till round 9. Except for the fact that in round 10, I am having only 3 operations. Similarly, for decryption process also, if you start giving the ciphertext as an input, after the round key structure, we have 9 rounds which will have all the 4 operations here, and then followed by the 10th round, which consists of only 3 operations. The operation that is missing is your mixed column operation here. We don't have a mixed columns in your 10th round. So this is the overall structure of AES. You can see this is how the encryption starts. We start with an AddRound key followed by 9 rounds of 4 operations each, and then we close it off by a 10th round with only 3 operations. This is how the key is also expanded. Anyhow, once we will discuss each and every one of these operations in detail. So you'll have a better idea on what is happening inside. So 4 different stages are used. As I told you, there are 4 operations, isn't it? 4 different stages are used. 1 of the permutation and 3 are for substitution. So any guesses which is your permutation and which is substitution? The first one is substitute bytes. I have told you about the S boxes. We did study about the S boxes during DES and also simplified AES as well. So here also we use an X box to do a simple substitution technique. Whatever byte is there, a byte by byte substitution we perform according to a S box that is fixed for AES algorithm. Next comes shift rows. So here we simply shift or change the order of the bytes. We'll discuss this with an example, no problem. So this is your permutation. Because I'm not going to change anything, I'm only just changing the order of your state matrix and the remaining 3 operations, which is your substitute bytes, which is your mixed columns, and which is your AddRound key, form your substitution things. That means I change your original text. So substitute bytes changes your original text. Mixed columns, I'm going to do a matrix multiplication with a fixed matrix. And here I'm going to do a 4 by 4 matrix. I have shown you how this operation can be performed in SAES on a 2 by 2 matrix, isn't it? Now we are going to take a 4 by 4 matrix here. And then comes the AddRound key, which is nothing but you perform an exclusive OR operation with the current state matrix and the round key, which is generated by the key expansion algorithm. So these are the 4 operations that are part of your AES algorithm. Only the AddRound key stage makes use of the key. If you observe carefully, whichever key you are selecting, we are using that key only for this particular stage only. We are going to we are going to perform an exclusive OR operation here with the key. But just this operation doesn't give you enough security. Whereas the remaining 3 operations do provide the confusion, diffusion, and non-linearity, as well as in combination with the AddRound key, gives you efficiency as well as high security to the feature. If you remove this AddRound key, then there is no key component for your entire structure. But if you just keep this and you remove these 3 things, then the concepts which are required as per Shannon is your diffusion, confusion, and diffusion properties along with non-linearity are missing. So this structure involves all of these 4 together in a kind of alternating scheme, gives you the efficiency or provides you the efficiency to implement it, and also high security for this particular cipher. The next one is, as you know, each and every one of these stages is easily reversible. So the decryption algorithm is not identical to encryption and makes use of inverse shift rows. Of course, you might be wondering what is an inverse shift row. So here we perform a circular left shift. So in the inverse shift row, I perform a circular right shift. That's all. And then inverse substitute bytes. Here I'm going to use an S box to do the substitute bytes. And here I'm going to use an inverse S box. That's all. Nothing else. So these are all the operations that are inverse to what you do during encryption procedure. And then comes the inverse round key, where it is nothing but we are going to perform an exclusive OR. And then comes the inverse mixed columns, where I'm going to use another 4 by 4 matrix, which is an inverse of this particular matrix, which I am using in the encryption procedure. So you have to remember these things, that not the same operations, not the exact same operations are used during decryption, but we are going to use the inverse operations during your decryption process. And then the decryption algorithm makes use of the expanded key in the reverse order. This you already must have seen during your earlier one also. Let me show you. So here, if you see, the encryption procedure starts with the first round key or the key K0. And then for each and every round, you can write this is K1, and then this is K9, and this is K10, starting from K0. Now, the decryption algorithm, it starts with K10 first. So you have to use K10 in the first initially. So I'm going to use the same keys that we have generated during encryption, but only in the reverse order. So the final round of both encryption and decryption consists of only 3 stages, which is required to make the cipher reversible. So I told you, start with an AddRound key, then you draw 9 rounds. In all those 9 rounds, you have 4 operations, and then draw the 10th round, which will have only 3 operations. So this is just to give you an insight about the 3 different variants of AES. As I told you, this remains the same. The plain text block remains the same of 128 bits. Of course, this is written in bytes and this is written in words. So just to give you an idea, if at all when you're studying the theory, you might get 4 words or 16 bytes. Do not get confused. It is nothing but 128 bits. Your AES accepts 128-bit plain text and it uses a 128-bit key. That's all. Except for the fact that if you change the key size, if I selected the key size to be 128, then my number of rounds will be 10. And similarly, if I select the 192 key size, then my number of rounds will become 12. And similarly, with the increase in the rounds, I need to perform the key expansion algorithm to give me more number of words. So if I choose the 256 key bit size, then I will have the number of rounds as 14, and the number of keys that I have to generate is also higher. So these are some of the AES parameters for the 3 versions of the AES that we usually study. But for now, I'm going to go with this most commonly used one, the 128-bit or AES 128, which uses the 128-bit key size. Of course, the plain text size is fixed. Now let us start studying about each and every one of those operations in detail. The first operation is called as substitute bytes. We did this earlier also. The substitute bytes is nothing but it is a simple table lookup. You have the AES defines a 16 by 16 matrix of byte values called an S box that contains a permutation of all possible 256 8-bit values. So whatever 8-bit values are there, I have all possible combinations. Let me show you the S box of AES. This is your S box. You can see all the possible 8-bit combinations are written down here. These are 4 bits and these are 4 bits, isn't it? So all the combinations are written down here. So what does your substitute bytes do? What it does is it will simply select. So each and this is your state matrix. So if this is your 128 bits of plain text written as a state matrix, isn't it? So I told you there are total of 16 boxes. Each box has got 8 bits. So each one of these things is a byte. So each and every one of these bytes is given as an input to the S box. And let me take an example here. So if I have something like my first byte is AB. This is my byte. So this is 4 bits and this is 4 bits. The first 4 bits will tell me the row and the remaining 4 bits will tell me the column. So A is my row and B will be my column. This is my column. So the answer will be, and this AB will be replaced with 62. You can see this. Each individual byte of state is mapped into a new byte in the following way. You have to map each and everything with a new one. The rule that we take is the leftmost 4 bits of the byte are used as a row value and the rightmost 4 bits are used as a column value. So these row and column values serves as indexes into the S box and to select the unique 8-bit output value. Let me show you an example to understand this in a better manner. Okay. Now, this is an example which is given in the textbook. My state matrix contains something called as an EA. As I told you, the first 4 bits, which is E, form the row. And my next 4 bits, which is A, form the column. So where is E? This is E here. And where is A here? This is A here. So what it is? This is the value which I should be replacing it with. So EA is now replaced with 87. Similarly, let me check another one. I have something called as 0, 4. So 0 is here, a row, and 4 is here. So automatically 0, 4 will be replaced with F2. So there you go. This is what we call as substitute bytes. Each and every byte I am going to replace with a new byte from the S box according to the rules. The first 4 bits form the row and the next 4 bits form the column. Look for the intersection and replace this byte with this one. That's all. So this is called as your substitute bytes, which makes use of an S box in AES. The next operation is pretty simple, which we call it as a shift row transformation. So the forward shift row transformation called shift rows is shown below. See, this is once again the state matrix. This is my original state matrix. And if I want to implement the shift row operations on this matrix, the first rule is keep the first row as it is, untouched. So I'm not going to change anything in the first row. See, S00, 01, 02, 03. It is exactly the same. For the second row, you perform a left circular shift of 1 byte. So this S1, 0 will be moved towards the last. So S1, 1 comes first, S1, 2, followed by S1, 3, and then S1, 0. For the second row, so the third row, you take the first 2 bytes and then shift them circularly to the left. So what will happen? My resultant will be S2, 2, S2, 3, followed by S2 comma 0 and S2 comma 1. And for the last row and your fourth row, what you do is you replace the entire first 3 bytes circularly. I don't say replace, you just move them. So the first one will be S33, S3 comma 0, S3 comma 1, and S3 comma 2. So the shift row, what it does is the first row of the state is not altered. For the second row, a 1 byte circular left shift is performed. For the third row, a 2 byte left circular shift is performed. And for the first row, and for the fourth row, a 3 byte circular shift is performed. That's it. Very pretty simple, isn't it? You are simply changing the positions. As I told you, this is the one permutation operation that is performed during the rounds. And I'll show you an example. So this is my state matrix. So if I'm going to perform a shift row operation, just check it out. This is exactly the same. For this row, I have to move this byte as a circular shift. So this byte goes to the last, which gives me what? 6E4C90 EC. So this has moved. And similarly, for my third row, these 2 bytes have to be moved towards the back. So 46E7 4SE3. And for this, the first 3 bytes are left circular shifted. So which gives me this. So A6, 8C, D8, 95. So this is the output. Now this is the state matrix after performing the shift rows function. And the inverse of this, which we call it as the inverse shift rows, it performs the circular shifts in the opposite direction. What do you mean by opposite direction? If I'm doing it in towards the left, then I have to do it towards the right. That's all. I have to do it in the, you can see this performs the circular shift in the opposite direction for each of the last 3 rows with a 1 byte circular right shift for the second row and so on. So for similarly, as you just shifted 1 row towards the left here, during the decryption procedure, you shift 1 row, you shift 2 rows, you shift 3 bytes. I'm saying rows, it's bytes. So 1 byte from second row, 2 bytes from third row, and 3 bytes from fourth row during the decryption procedure, not to the left, but to the right hand side. So this is your shift row operation. Okay. Moving on. Next comes your mixed columns operation. What do you mean by mixed columns operation? If you remember the AES lecture well, mixed columns operations deal with matrix multiplication. So each byte of a column is mapped into a new value that is a function of all 4 bytes in that column. The transformation can be defined by the following matrix multiplication on the state matrix. This is your state matrix, isn't it? So this is your state matrix. And this is your 4 by 4 matrix. You have to perform a matrix multiplication so that you will get the resultant state now. To perform this matrix multiplication, it is not done just as a numerical values. You can see each and every column will be multiplied to get the resultant new columns. If you know matrix multiplication, you can simply write these things as, I'll show you. Each element in the product matrix, this is 1, is the sum of products of elements of 1 row and 1 column. So if you see here, this row into 1 column, and in this case, the individual additions and multiplications are performed in the Galois field of 2 power 8. The mixed columns transformation on a single column of state can be expressed as, so for that case, S0 comma j is equal to 2 into so and so plus 3 into so and so, because these are 2 ones here, plus S2 comma j plus S3 comma j. Let me take you a numerical example and I'll show you how the mixed columns work. This is nothing but matrix multiplication, that's all. So this column, if you say this is the column and you multiply with this row, gives you this value. That it says, that is the reason it says that sum of the products of elements of 1 row and 1 column. 4 by 4 matrix into 4 by 4. Now let me show you. This is the example which we are working on, also given in the textbook. So let me put a dot here. This is your given matrix. This is your state matrix. Now this is the resultant product matrix after doing the mixed rows transformation. How did you get it? Now, in order to get this value, this particular column value, this is the operation. You can see 02 into 87, exclusive odd with 03 into 6e, exclusive odd with 1 into 46 gives me 46, exclusive odd with 1 into A6 gives me A6. So this gives you as a resultant of 47, and 47 will be copied here. Similarly, to get the 37 value, you can see 87. So you can see this 87 plus 02 into 6e, this one. This is the row I'm talking about. This row into this column. 02 into 6e, exclusive odd with 03 into 46 or 46, exclusive odd with 1 into A6 gives me 37. Let me show you how do you get this 47, and then maybe you will be able to understand, or you may be able to do the remaining ones yourself. So as I mentioned before, the individual additions and multiplications are performed in the Galois field of 2 power 8 with the generator polynomial, or with the irreducible polynomial selected for AES as x power 8 plus x power 4 plus x cube plus x plus 1. What this tells you is any of these operations, if it has a degree more than x power 7, it has to be reduced using this polynomial. Any degree less than x power 7 is okay, because I'm only having 2 power 8. Okay, now let me show you. So 02.87, this dot represents the multiplication in Galois field of 2 power 8, and this represents the exclusive OR operation. So 02 into 87 plus 03.6c, exclusive OR with 46 and exclusive OR with A6. Now, to do this, first let me start with this particular point. Let me start with this 02 into 87 part. Okay, so if I start with 02 and 87, how do I write 02? 02 in binary is 0, 0, 1, 0. Of course, there is a 0 here. That means all zeros. Similarly, 87 can be written as. Tell me, what do you mean by 87? It is 1, 0, 0, 0. 7 is 0, 1, 1, 1. Now, if you take, this is x power 0, this is x power 1, this is x square, and this is x cube. There is no x cube component, there is no x square component, there is a 1 for x component. So 02 can be written as x, and 87 can be written in a polynomial way as, this is the x power 7 component. If you write it down, x power 0, x power 1, x square, x cube, x power 4, x power 5, x power 6, and x power 7. Take this down. Now, there is a 1 for x power 7, so x power 7 plus. There is a 0 component for x power 6, 0 for x power 5, 0 for x power 4, 0 for x power x cube. And there are 3 ones. So I have the components of x square plus x plus 1. So this 02 into 87 can now be written as x into x power 7 plus x square plus x plus 1, which gives me the resultant of x power 8 plus x cube plus x square plus x. If you see, the degree of this value is greater than x power 7 or is greater than 7, which I cannot accept because I have only 8 bits. So for this purpose, I have to reduce this resultant value according to the modulo of this. What I mean is, I have to find out x power 8 plus x cube plus x square plus x mod this x power 8 plus x power 4 plus x cube plus x plus 1. Because this degree is more, I cannot accept it. I have to reduce it. So what do? I'll simply write like this. X power 8 plus x cube plus x square plus x. This is my way of doing it. So x power 8 plus x power 4 plus x cube plus x plus 1. There is an x power 8 here. So I'll just multiply it with 1. X power 8 plus x power 4 plus x cube plus x plus 1. Now, because I am talking about the arithmetic being done in Galois field of 2 power 8, similar elements cancel each other out. So x power 8 is gone. Similarly, x cube is gone and x is gone. write down the remaining elements. The remaining elements that I get out of this is x power 4 plus x square plus 1. So how do I write this in binary? There is no x power 7 component, so 0. There is no x power 6 component, 0. There is no x power 5 component, 0. There is an x power 4 component, 1. There is no x cube, 0. There is x square, 1. There is no x, and there is x power 0, so 1. So this 02.87, 02.87, now I have got the resultant value as 0.0101. Similarly, I have to perform for 03.6e, and I have to perform all these things. So let us check out how to do these things. The next one is, now let me write down the first value which I obtained already, which is 0.0.0.1. 0.1.0.1. This I already got it from, this is a value of 0.2.87. So this is the value. Now let me perform the same kind of operations on 03 into 6e as well. So 03 can be written as, in binary, what is 03? 03 is nothing but 0, 0, 1, 1. Of course, that is the first 0 here, all zeros. So this can be written as, there is no x cube, so there is no x square. So x plus 1. Similarly, if you take 6e, this is 6, this is e, isn't it? So if you write this down in binary, there is no x power 7. And give me a second, I think I made a small mistake here. This is x power 6. Okay, let me write this down. This is x power 6 plus what? X power 5 plus, there is no x power 4, there is x cube, there is x square, there is x, ignore this. Okay, so this is what. Now 6e is written like this. Now to perform 03 into 6e, what I need to do is x plus 1 into x power 6 plus x power 5 plus x cube plus x square plus x. What is the resultant value? Find it out. First, let me multiply with x, which gives me x power 7 plus x power 6 plus x power 4 plus x cube plus x square, isn't it? Now, continue. Now you multiply with 1, which gives me x power 6 plus x power 5 plus x cube plus x square plus x. Find out what the similar elements are and then remove them. Okay, and then remove them. You can see that there is an x power 6 here, x power 6 both are gone, and x cube is gone, x square is gone. So what are the elements that are remaining in this? It is x power 7 plus x power 5 plus x power 4 plus x. Write this down in binary. X power 7 component is 1, no x power 6, x power 5, x power 4, no x cube, no x square, x is there, no x power 0. So 03.6e can be written as 10110010. What are the remaining two ones? Remember, this I got the value already. This I got the value. This I got the value. 4, 6, I can directly write them as what? Tell me. 4, what is the value of 4? 6. 0, 1, 0, 0. 6 is 0, 1, 1, 0. What is A6? 1, 0, 1, 0, 0, 1, 1, 0. Now we have to perform an exclusive OR for all these 4 values. Let me show you. So this is this 0001, 0101. This value which we just got is here 1011, 0011, and this 46 value in a hexadecimal to binary. Similarly, A6 value from hexadecimal to binary. Perform an exclusive OR. So 000011, 110, 1, 1, 110, 000, 011, 1. All zeros, 0. 0 0 0 0 1 1 1 1 0 1 0 1 1 1 0 0. So 0 1 1 1 0 1 1 0 1. So 1 0 1 1 1 0 0 0 0. So according to the truth table, you just find out. So this is the value. If you convert this into hexadecimal, what is the value here? 0 1 0 0 is 4. This is 7. See, we did the same calculation and we got the value as 47. Got it? So what I did was pretty simple here. I simply calculated all these values. I did an exclusive OR, so I got the value as 47. Similarly, you can try to do the remaining calculation. This we verified. You can try these values as well. 87 exclusive orbit 02.6e exclusive orbit 03.46 exclusive orbit A6 to check whether you are receiving or whether you are getting the same 37 or not. In this way, the entire state matrix will be getting will be changed after your mixed columns operation. Now, as I told you, for decryption, we have something called as an inverse mixed columns. There's a different matrix that we use for that. So this is the inverse mixed columns matrix 0E 09DB. This is a 4x4 matrix which is used during your decryption process. So if you multiply your original matrix and this, you get an identity in the Galois field of 2 power 8. So this is the one which we have to use for decryption process. So this is your mixed columns. The next one is your AddRound Key transformation. This is a straightforward one. Where you do is you have your whole 128-bit key state your state matrix, and you have your 128-bit round key. Simply perform a exclusive OR operation. You can do this as a column-wise operation. You can check this out. So S00, 10, 20, 30 you can exclusive OR with WI, which gives you a resultant matrix. Similarly, this column you can do with this, and you can get with here. So this transformation is as simple as possible, which helps in efficiency, but it also affects every bit of the state, because each and every bit that is there in the state matrix is now getting operated on with this exclusive OR operation. It affects the entire all the bits in this state matrix. This is your original state matrix. This is your round key, and then this is your resultant matrix. Let me show you a small example, the one which you did earlier. So this is your state matrix, and this is one of your round keys. So how do you do? How did you get EB here? If you take 4, 7 is nothing but 4 is 0, 1, 0, 0. 7 is 0, 1, 1, and AC. A is 1, 0, 1, 0. C means put in 1, 1, 0, 0. Okay. That was 12. So if you perform an exclusive OR, what do you get? 1, 1, 0, 1, 0, 1, 1, 1. So 1, 1, 1, 0 is E, and 1, 0, 1, 1 is 11B. So you can see E and B. I got the values, isn't it? So this is how you perform an exclusive OR operation. So each column is performing an exclusive OR operation with each column. Thereby you will get the resultant column. So the inverse AddRound Key transformation is identical, simply because exclusive OR operation is an inverse in itself, because the exclusive OR operation is its own inverse. This is a straightforward operation in AES. There is nothing much here. You simply take the state matrix, you simply take your round key, and then you perform the exclusive OR operation. This is the summary of what we did till now. As I told you, your AES, when you opt for a 128-bit key, it has 9 full rounds of 4 operations each, and 1 round with 3 operations each, and it starts with an AddRound Key operation, isn't it? So this is what you can see. This is your state matrix of 128 bits arranged into 16 boxes of 8 bits each, or bytes. This you perform a substitute byte operation where you are going to use an S box which is fixed, and after the substitute bytes, then you are going to perform a shift rows operation where we are going to just change the positions of your bytes, and then you perform a mixed columns operation where you are going to use this matrix fixed, and then finally you are going to perform an AddRound Key operation where you use a distinct round key for every one of your rounds. You can see these are your constant inputs, your S boxes and mix columns, whereas the round key changes for every round. So the structure of a single AES round can be summarized. This is how it is done. The algorithm begins with an add round key stage, followed by 9 rounds of 4 stages and a 10th round of 3 stages. This applies for both encryption as well as decryption also. And both of them are inverse of its counterpart. Whatever we are doing in encryption, the operations that we do for your decryption process is an inverse. So that is the reason this cipher works, and it is also efficient for implementation purposes also. Okay. Now, this is until now we discussed about how the cipher works, what are the different operations that are involved in AES. Now let's talk about how do you expand the key. Okay. So as I told you, AES accepts a 128-bit key. Now this key, it will be given as an input to your first round or the first AddRound key operation. And from this input key, we start expanding this to suit our needs. Now, if my AES is going to have a 10 round structure, then I have to generate 11 round keys. First key for the initial AddRound key, and then 10 different keys for the 10 different AddRound operations that are there in all your 10 rounds. Now, if you can see here, the AES key expansion algorithm takes as input a 4-word 16-byte key and produces a linear array of 44 words. We usually refer the key in the form of words because it is easier to do the calculations. And each key, if I'm saying that for one round, the first round, if it is K0, it consists of 4 words, W0 till W3. So each word is 32 bits. Each word is 32 bits. So this provides a distinct 4-word round key for the initial AddRound key stage and each of the 10 rounds of cipher. Now, this is how the algorithm works for key expansion. This is your original 128-bit key. These are written down into 4 words. You can see W0, W1, W2, W3. So each of these words are 32 bits each. And from these first 4 words, you start generating the remaining keys for all your other rounds. So this is K0. This is K1. Similarly, you have to go till K10. Isn't it? This is for your 10th round, round 10. This is the one which is used for round 10. You can see that the words which are powers of 4 or which are multiples of 4, W0, W4, W8, W12, W16, 20, so on till W40 are actually generated using a complex function G. I'll show you that. Give me a second. So the key is copied into the first 4 words. This is your first 4 words of the expanded key. The remainder of the expanded key is filled in 4 words at a time. So for each round, you generate the next 4 words, next 4 words, next 4 words, and so on. Now, each added word, Wi, depends on the immediately preceding word Wi-1 and the word 4 positions back, Wi-4. If you don't understand the statement, just check this out. What am I getting from W4? How am I getting W4? W4 is nothing but an exclusive OR operation between W0 and W3. Similarly, W5 is an exclusive OR operation between W4 and W1. So each key or each word is dependent on the word preceding it. W5 is dependent on W4, W6 is dependent on W5, W7 is dependent on W6, and there are 2 things. Another one is I-4. If you see here, W7 is on W6, the key preceding one, and 7-4 gives me W3. So W3 is the input for W7. Similarly, W6, 6-4, W2. So each and every word is obtained by an operation between the word before it and also the word 4 positions from it. Okay. For a word whose position is in the W array is a multiple of 4, as I told you, W0, W4, W8, W12, W16, we use a more complex function G. What is this function G? We did a simple example for simplified AES where more or less the functions are same except for the fact that we worked on a 16-bit key. I have shown you these operations only. Here also, let me explain how it is being done. The initial word is 32 bits. A single word is 32 bits. So if you take as a G as an input here, I am going to explain this. What is this G function? Isn't it? So if I give W3 as an input to G, There are 32 bits in W3, isn't it? Those 32 bits are divided into 4 bytes, 4 8s. And then this is nothing but the rotate word operation, where the first byte is left circular shift. So B0 goes to the back. The B0 goes to the back. This is called as rotate word. You can see here. The first one is rot word or rotation of word, performs a 1 byte circular left shift on a word. This means that an input word B0, B1, B2, B3 is transformed into this. B0 goes to the back. So B1, B2, B3, B0. That is what I do here. This is your rot word function. Then you get the remaining bytes. And here we have something called as the sub word, where each word, which is once again 8 bits, will be given as an input to your S box. The same S box is used just like what we did for encryption. Because here also I'm having an 8 bits. The first 4 bits will give me the row. The remaining 4 bits will give me the column. And each byte will be substituted with a new byte from the S box. And then the third function, which is done in the G, is the third operation is you have to perform an exclusive OR with the round constant RCJ. The resultant of steps 1 and 2 is exclusive OR with round constant RJ. So what is this round constant? How do you get it? That is the last one which we will discuss in AES. So the round constant is a word in which the 3 rightmost bytes are always 0. Because I need a 32-bit constant, you have to understand this. The first byte in this, the first 8 bits are calculated, and the remaining 8 and the remaining 3 bytes, which are the 24 bits, are all zeros. So the round constant is different for each round and is defined as, so round constant J is equal to RCJ. This is the value followed by all zeros. With RC1 is given as 1, RCJ is equal to 2 dot and RCJ minus 1. So 2 into RC1. So here once again we have to perform these operations on Galois field of 2 power 8, as we just shown you how to do in mixed columns. So these are the different round constant values for all the 10 rounds. Round 1, 0, 1, round 2, round 3, round 4, round 5, round 6, round 7, round 8, round 9, and round 10. So this is how I get the operation of G for all the different rounds. For all the different rounds, I have a separate and a different round constant to use. So this forms the first byte, where the remaining 3 bytes are all zeros. So the Rijndael developers designed the expansion key algorithm to be resistant to known cryptanalytic attacks. The inclusion of a round-dependent round constant, as was I said, for each round. So when I'm calculating round 2, I use this. When I'm calculating round 3, I use this. Round constant eliminates the symmetry or similarity between the ways in which round keys are generated in different rounds. That means I'm going to make it more difficult to cryptanalyze. The reason why I selected, or why these guys have selected different round constants to be used for different rounds, is to simply make, or to simply clear away any symmetry or similarity during your key expansion process. So there is another example. So if you have, let us assume that this is my K8, which I am using for round 8. So if I want to calculate for K9, so this I is nothing but the word. So I'm first starting with W36. So this, I will take this value here first in temp, and then I will perform this, because this is the one which I will perform a G operation on, isn't it? So this word is given as an input to G. So in G first, I will perform the rotate word operation. So this 7F goes to the back, you can see. And then I perform the substitute bytes operation or substitute word using the S box, and round constant 9. You can see that it is 1B here, and 1B, and all the remaining ones are zeros. So all the remaining ones are zeros, 1B, 0, 0. So after doing this, I perform an exclusive OR operation with this. You can see I perform exclusive OR operation with this. And then finally, I have my WI-4, because for each and every word is dependent on the previous word along with the word which is 4 positions away from it. So WI-4, which is nothing but 32. So all this I perform an exclusive OR. Now I get this word. So similarly, I have to do it for W37. If I want K9, then what I have to do? W36, I calculated, then W37, W38, and W39 gives me K9. For K10, the same thing goes on from W40. Okay, so this is how you perform the key expansion in AES. Hopefully you understood this, and once again thank you for watching, and if you have any queries regarding this, you can always ping me in the comment section. So please remember that once again suggest you to please go back to the SCAES first, check out the operations there. These are very much similar operations, except for the fact that we do it on a large scale. SAS performs it on 16 bits, whereas the original AES algorithm performs it on a 128 bit. That is the only difference. So with that, thank you and good luck.